Hello and good afternoon friends, welcome once again to the CEC-UGC live lecture. Dear friends, in this session today we are going to talk on the subject called chemistry, and for all the lovers of chemistry I would like to tell you all that we are carrying a series on chemical reactivity and mechanism, and under this very series today we are going to talk about aldehydes and ketones. And for this again we have with us in our studios Dr. Vandana. She is Assistant Professor in Department of Chemistry, Dayal Singh College, University of Delhi. So taking advantage from her experiences, let's understand about what aldehydes and ketones are. Hello ma'am, welcome to the EduSet lecture. And as we are carrying this series and we have conducted numerous lectures on chemical reactivity and mechanisms, today through you we want to know about what aldehydes and ketones are.
Thank you so much Geetika ji, and good evening viewers. Aldehyde and ketones are the important functional group of chemistry. So these are the important compounds which we can synthesize, and we can understand their chemical reactivity, how they can synthesize, how they can react for further applications. As we know, the synthesis of any organic compound is how much important, and to synthesize a desirable compound is more important. So if we know the chemical reactivity and mechanism of a synthesis, it is best part for us. So today in this series of chemical reactivity and mechanism, we will discuss about the aldehydes and ketones. These are the important functional group of chemistry. What are aldehydes and ketones? Aldehyde and ketones, we can say also alkanals and alkanones. Compounds that contain the carbonyl group are called carbonyl compounds. The carbonyl compounds are broadly classified into two categories, aldehydes and ketones. What are aldehydes? RCHO, when carbonyl having one R group and one hydrogen group, and ketones when both the valencies of carbonyl carbon are satisfied with alkyl, aryl or any other group. Second, carboxylic acid. What are carboxylic acid? RCOOH, and their functional derivatives when OH is substituted by the groups like halogen, like OR, like OCOR and NH2. When we replace with halogen or hydroxyl group, it will acyl halide, and when we will replace by OR group, this is ester, and when we will replace OH group by OCOR, it is anhydride, and when we replace NH2 group, it will be amide. What are aldehydes? Aldehydes are the carbonyl compounds, where as I have already stated, in which carbonyl carbon is bonded to a hydrogen and a hydrocarbon group, such as it can be alkyl, aryl, alkenyl, cycloalkyl etc., or a second hydrogen. Ketones are the carbonyl group compounds in which carbonyl carbon is bonded to two hydrocarbon groups. If the two hydrocarbon groups are identical, the ketone will be symmetrical. If the groups are different, it will be unsymmetrical. You can see in the structure that what is the carbonyl group, what will be aldehyde, what will be symmetrical ketone, and what will be unsymmetrical ketone. In saturated aliphatic aldehyde, the aldehyde group is bonded to an alkyl group or hydrogen atom. In case of formaldehyde, hydrogen atom. While in saturated aliphatic ketones, the carbonyl carbon is bonded to two alkyl group. Both of them have general formula CnH2nO. In aromatic aldehydes, the aldehyde group is directly bonded to the carbon atom of the aromatic ring. While in aromatic ketones, the carbonyl carbon is bonded to at least one aromatic ring. In cyclic ketones, the carbonyl carbon is a part of the ring system. Now we discuss about the nomenclature of aldehydes and ketones in details. According to IUPAC system, the saturated aliphatic aldehydes and ketones named as alkanals and alkanones for ketones. The position of the ketone group is first indicated and then by suffix -on. The common name of an aldehyde is obtained from the common name of corresponding carboxylic acid by replacing IC acid by aldehyde. The common name of ketone is obtained by citing the name of the alkyl or aryl in alphabetical order and then adding a separate word ketone. For example, here are the 3 examples like CH3, CH2, CHO, it is propanol or propanedihyde, a saturated aliphatic aldehyde. Second one, pentane 3-on, it will be on because the carbonyl group, ketonic group is on 3rd position, diethyl ketone, a saturated again aliphatic symmetrical ketone. Next, 5-methyl-hexane 3-on, ethyl isobutyl ketone, again a saturated aliphatic unsymmetrical ketone because both the R group which is attached to the carbonyl group are different, that is why it is called unsymmetrical ketone. When the groups are same, it will be symmetrical. When the aldehyde is attached to a ring, a suffix carbaldehyde is added to the name of hydrocarbon. The aldehyde C6H5CHO has the common name benzaldehyde and is accepted by IUPAC. The cyclic ketones are named as cycloalkanones. Aromatic ketones are named from the common name of the carboxylic acid by replacing the ending -ic with the O-phenone. Here are the examples for nomenclature like benzene carbaldehyde, we are adding carbaldehyde. So, benzaldehyde an aromatic aldehyde, cyclopentane carbaldehyde, cyclopentanone a cyclic ketone, 2-methyl cyclohexanone a cyclic ketone, acetophenone it is an aromatic ketone or we can say it is methyl phenyl ketone. Next, butyrophenone or phenyl normal propyl ketone an aromatic ketone, benzophenone or we can also say a diphenyl ketone an aromatic ketone. Structure of carbonyl group. The carbonyl group in aldehydes and ketone consists of a carbon-oxygen double bond. The carbon of carbonyl group and the oxygen are both sp2 hybridized. One of the 3 sp2 hybrid orbitals of carbonyl carbon overlaps linearly with one of the 3 sp2 hybrid orbitals of oxygen to form a carbon-oxygen sigma bond. The remaining 2 sp3 hybridized sigma bond atoms in a saturated ketone by sp3 orbital overlap. In a saturated aliphatic aldehyde, one of the remaining 2 sp2 orbitals of the carbonyl carbon forms a sigma bond with a hydrogen atom by sp2 of the carbon and 1s orbital of the hydrogen atom by overlapping, and the other atom forms a sigma bond with a sp3 hybridized carbon by sp3 orbital overlapping. In formaldehyde, however, both sp2 orbitals of carbonyl carbon form CT bonds with 2 hydrogen atoms. The remaining 2 sp2 orbitals of oxygen accommodate 2 unshared pair of electrons. Finally, the p orbital of sp2 hybridized carbonyl carbon overlaps laterally with the p orbitals of sp2 hybridized oxygen atom to form a pi bond. It is not N, sorry, it is a pi bond between carbon and oxygen. Thus, a carbon oxygen double bond of the carbonyl group consists a sigma bond and a pi bond. The carbonyl carbon and the other 3 atoms bonded to it lie in one plane, and the bond angles around the carbonyl carbon are approximately 120 degree, which you can see in the figure that first bond angle is the sigma, second is the pi bond, and the bond angles is 120 degree, and there are 2 lone pair electrons on oxygen atom. The pi electron cloud is situated above and below the plane extended between carbon and oxygen as shown in the figure. Due to the greater electronegativity of oxygen related to the carbon, the pi electron cloud is somewhat drifted towards oxygen. This causes the carbonyl carbon to acquire a partial positive charge and a oxygen negative charge, a partial negative charge. This explains the electrophilic character of carbonyl carbon and the substantial values of dipole moments of carbonyl carbon. And you can see that at carbon there is a pi bond formed by laterally overlap of the sp2 hybridize of oxygen orbital and carbon orbitals. The polar character of carbon-oxygen double bond is also explained on the basis of resonance between the following Lewis structures. You can see the resonance contributor of a carbonyl group and the hybrid also. The structure of carbonyl group in terms of resonance structure, you can see the acetaldehyde and the different groups are there, HCOC, bond angle, bond length for different bonded groups. Now we are talking about the different isomers of aldehydes and ketones, like isomers having the molecular formula C2H4O. There are 3 isomers for this particular molecular formula. One is acetaldehyde. You know what are isomers? Isomers are the compounds having the same molecular formula but the different structures. So there are 3 isomers for this particular molecular formula: acetaldehyde, vinyl alcohol and epoxy ethane. For C3H6O molecular formula, there are 7 isomers. You can see one is exists in 2 enantiomeric form. You know what is the enantiomers? Enantiomer are the compounds which are stereochemically different. They are having the same structure formula. All the chemical properties and physical properties are same except the rotation of the optically light. So you can see here the 7 isomers of the particular molecular formula C3H6O. One is propanol, or we can say propionaldehyde, another one is propanone, acetone, propane 2-ene-1-ol, allyl alcohol, methoxyethane, methyl vinyl ether, cyclopropanol, 2-methyl-oxyrane and oxytane. For molecular formula C5H10O, following are the isomers. First one is pentanol, 2-methyl-butanol, 3-methyl-butanol, 2,2-dimethylpropanol, pentane 2-on, 3-methylbutane 2-on and pentane 3-on. For molecular formula C4H5O, these are the 3 isomers: butanol, 2-methylpropanol, butane 2-on. And for molecular formula C5H10O, pentanol, 2-methylbutanol, 3-methylbutanol, 2,2-dimethylpropanol. For 2-methylbutanol, 2 enantiomers are possible: pentane 2-on, 3-methylbutane 2-on, pentane 3-on. Now we come to the next part of the aldehydes and ketone, the preparation of these important functional groups. Oxidation. First we will discuss about the oxidation of alcohols with chromic acid. Aldehydes and ketones can be prepared by oxidation of primary and secondary alcohols with potassium dichromate in dilute sulfuric acid. You can see in the example that ethyl alcohol, when react with potassium dichromate in acidic medium, it will give acetaldehyde, and isopropyl alcohol will give acetone. Cyclohexanol will give you cyclohexanone, or butane 2-ol give butane 2-on. Aldehydes are very sensitive to further temperature above the boiling point of desired aldehyde but below that of the alcohol. You can see in the reaction that propane 1-ol has boiling point 97 while propanol has boiling point 49. The aldehyde distills out as it formed and escapes further oxidation. This is possible because aldehydes boil at lower temperature than the corresponding alcohol, which is also shown in the reaction. However, this method is successful for aldehyde that boils significantly below 100 degree Celsius. There are 2 examples. One is for propane 1-ol whose boiling point is 97 degrees Celsius, which produce you propanol whose boiling point is 49 degrees Celsius. So, aldehyde has lower boiling point than corresponding alcohol. Next example is butane 1-ol, which having boiling point 118 degrees Celsius, and butanol will produce which is having boiling point 76 degrees Celsius. So, we should keep in mind these conditions. Ketones are not oxidized further unless very vigorous conditions. Vigorous conditions are related to the temperature, pressure and the chemical reagents. About the chemical reagent, John's reagent. What is John's reagent? A dilute solution of chromium oxide in dilute H2SO4, which oxidizes secondary alcohols in acetone at 15 to 20 degrees Celsius to give the corresponding ketones. And the important part of this is that without affecting the double or triple bond, it also oxidizes primary alcohol to corresponding aldehydes. What is mechanism? Chromic acid oxidation of involves a rapid reversible, there is a reversible formation of chromate ester. First of all, potassium dichromate when react with acid, it will form H2CrO4 chromic acid, which will then react with 1 degree alcohol to form a chromate ester, followed by cleavage of carbon, hydrogen and a alpha carbon in the chromate ester to produce the corresponding aldehyde. Next, oxidation of alcohols by Collins reagent and Corrèze reagent. What is Collins reagent? It is a complex of chromium oxide and pyridine. What is Corrèze reagent? It is pyridinium chlorochromate, we can say it is PCC short form, by mixing chromium oxide pyridine and concentrate HCl. And pyridium dichromate, it is PDC in short form. These oxidations are usually carried out in methylene chloride solvent at 25 degrees Celsius temperature. These are mild oxidizing agent and do not oxidize aldehydes further and do not affect carbon-carbon double bond and triple bond that may be present in the molecule. Manganese oxide is also a fairly specific reagent for the oxidation of alcoholic group and is often used to oxidize allylic alcohol to alpha beta unsaturated aldehydes and ketones, the benzylic alcohols to corresponding carbonyl compounds. Alcohols containing acid sensitive functional group such as epoxide or acetyl are usually oxidized by PDC or Collins reagent. Here are the examples. You can see in the reaction that epoxides and the other compounds alcohol are oxidized by Collins reagent to the corresponding aldehyde without affecting the other groups, which may be acetyl group, it may be unsaturated group, it may be epoxide group. There are other examples. You can see that PDC, potassium dichromate and manganese oxide and pyridinium chlorochromate oxidize exclusively to the corresponding aldehyde without affecting the other function group present in the alcohols. Like trans-cinnamyl alcohol oxidized to trans-cinnamaldehyde and racemic cyclohex 2-in-1-ol oxidized to cyclohex 2-in-1-on with the help of pyridinium dichromate and DMF at 0 degrees Celsius, and trans-crotyl alcohol with manganese oxide changes to trans-crotonaldehyde, while benzyl alcohol oxidized to benzaldehyde in methylene chloride. Opener oxidation of alcohols. It is usually employed for oxidation of secondary alcohols to ketones. It consists of heating of secondary alcohol with a large excess of acetone or cyclohexanone in presence of aluminium tertiary butoxide as a catalyst. The secondary alcohol is oxidized to ketone at the expense of the reduction of acetone to the isopropyl alcohol or cyclohexanone to cyclohexanol. You can see in the reaction that there is a conversion of 2 alcohol to isopropyl alcohol. It is particularly useful for oxidizing unsaturated secondary alcohols because it does not affect the carbon-carbon double or triple bond, means unsaturation. Unsaturated primary alcohols may also be oxidized to unsaturated. Aldehydes, by replacing acetone with para-benzoquinone, the beta gamma unsaturated secondary alcohols undergo oxidation with the migration of double bond to form alpha beta unsaturated ketone. You can see in the reaction that but 3-ene-2-ol can convert it to but 3-ene-2-one. And in the another there is a shifting of migration of double bond to alpha beta unsaturation from beta to gamma. Catalytic dehydrogenation of alcohols. Aldehydes and ketones can be prepared by passing the vapor of primary or secondary alcohols over copper at 300 degrees Celsius. Formaldehyde, acetaldehyde and acetones can be prepared by these methods. You can see in the reactions that formaldehyde can be prepared by methyl alcohol, acetaldehyde from ethyl alcohol and acetone from isopropyl alcohol at 300 degrees Celsius when passes over copper. Ozonolysis of alkenes. Ozonolysis means addition of ozone. Aldehydes can be prepared by reductive ozonolysis of symmetrically disubstituted alkenes. We have already said what is symmetrical. Symmetrical means when the groups are same. The ketones can be obtained by reductive ozonolysis of symmetrically tetra-substituted. Here is tetra-substituted alkene, or the group can be similar or different. In this process, the alkene is allowed to react with ozone at low temperature, usually minus 80 degrees Celsius in an inert solvent such as methylene chloride, chloroform, carbon tetrachloride or ethyl acetate to form ozonide. So, first of all we get the ozonide. Then ozonide is cleaved by the treatment with dimethyl sulfide or zinc with water. These are the examples. First of all, ozone combined with ethylene to form ethylene ozonide, and then it is cleaved to give a formaldehyde. Again 2-butene give acetaldehyde through 2-butene ozonide, 2,3-dimethyl 2-butene will give ozonide 2,3-dimethyl 2-butene, and which is cleaved by zinc to give acetone. Oxidative cleavage of vicinal glycols. Vicinal glycols, or we can say diols, means 2 hydroxyl group attached to the 2 adjacent carbon atom. When treated with periodic acid, which is HiO4, or lead tetraacetate, this is your lead tetraacetate, undergo oxidative cleavage at the carbon-carbon bond holding the 2 hydroxyl group to form 2 molecules of carbonyl compounds. When periodic acid we are taking for cleavage, it is called Malaprade reaction. When we are taking lead tetraacetate for cleavage of this bond, it is called Craigie reaction. Aldehydes are prepared by the oxidative cleavage of glycols of this type. RCHOH, CHOH, means both the group for diols are same. While ketones are prepared by the cleavage of glycols of the type, when there are 2 R group, they may be similar and they may be different. So, you can see in the reaction that butane 2,3-diol, or it is a racemic or meso, when reacts with periodic acid first of all combined, then there is a cleavage of carbon-carbon bond and you will get the 2 aldehydic molecules. Another example, 2,3-dimethyl butane 2,3-diols. We have already stated that you will get in this case ketone. There are 2 molecules of acetone formed here. When butane 2,3-diol reacts with lead tetraacetate, there is a formation of a complex, then further cleavage of the carbon oxygen bond and 2 molecules of acetaldehyde will form. In case of 2,3-dimethyl butane 2,3-diol, again 2 molecules of acetone will be formed with the help of tetraacetate lead. Glycols are obtained by the hydroxylation of alkenes with the cold dilute KMnO4 or osmium tetroxide. For example, you can see trans but-2-ene will give you butane 2,3-diol. The alkenes can be cleaved directly to carbonyl compounds without isolating the glycols by treating with an aqueous solution of sodium periodate and a trace of potassium permanganate or osmium tetroxide. It is called Luminex reagent. Hydration of alkynes. Acetaldehyde is prepared industrially by passing acetylene into dilute sulfuric acid containing a small amount of mercuric sulfate as catalyst at 60 degrees Celsius. Other 1-alkyl, it is alkynes. You can see that propyne, it is also called terminal alkynes. On hydration under similar conditions yield methyl ketones because the addition of water to a triple bond occurs according to Markovnikov rule. You know what is Markovnikov rule? The negative portion or hydroxyl group goes to that carbon which is having the less number of hydrogen atom. The hydration of symmetrical non-terminal alkynes yield a single ketone, but unsymmetrical non-terminal alkynes yield a mixture of two ketones. Hydroboration, oxidation of alkynes. The reaction of symmetrical non-terminal alkynes with boranes, hydrogens, and subsequent oxidation of addition product, it may be trivinyl borane with alkaline hydrogen peroxide yields a single ketone. Similarly, reaction of an unsymmetrical non-terminal alkyne yields a mixture of two ketones and hence is synthetically unimportant. You can see in the reaction but-2-ene, it is symmetrical, alkyne and non-terminal. In the previous reaction, you can see propyne is the terminal alkyne, while in but-2-ene it is symmetrical and non-terminal. There is a syn addition of THF, then a unstable compound is formed after the reaction with the hydrogen peroxide, and then you will get but-2-one. Another reaction is there, hex-3-ene will yield you hexane 3-one, not hexane, hexane 3-one. Aldehydes can be prepared by hydroboration oxidation of terminal alkynes. Again propyne is here. The overall result is an anti-Markovnikov rule, which I have already stated, just opposite to that of the Markovnikov rule across the triple bond. The hydroboration is carried out with disimyl borane instead of borane because borane may add twice to the triple bond of a terminal alkyne. So, disimyl bromine being bulking add to the triple bond and only one product will be there. Propyne when reacts with disimyl borane, it will give you propanol, and but-1-ene when reacts with the disimyl borane, it will give you butanol. It has their structure, you can see in the structure formula of disimyl borane. Pyrolysis of calcium salts of carboxylic acid. Formaldehyde can be prepared by heating calcium formate. Other aldehydes can be obtained by heating a mixture of calcium formate and calcium salt of a carboxylic acid other than formic acid. These are the examples. Calcium formate when heated give formaldehyde, and calcium acetate when react with calcium formate acetaldehyde will form, and calcium benzoate when react with calcium formate benzaldehyde will form. Ketones are prepared by heating calcium salt of carboxylic acid but not with the formic acid. These are the another examples for the preparation of acetone, pentane, pentane 3-one, benzophenone, cyclohexanone from calcium acetate, calcium propionate, calcium benzoate and calcium heptane dioate respectively with pyrolysis. Cyclopentanone can be obtained by heating calcium or barium adipate, and cyclohexanone can prepare by calcium heptane dioate, or we can say barium palmilate. Similar results can also be obtained by passing vapor of carboxylic acid over manganese manganese oxide MnO or thoria THO2 heated at 300 to 400 degree Celsius. Hydrolysis of geminal dihalides. Geminal dihalides means when two hydrogen atom attached to the same carbon atom with aqueous alkali. Ketones are obtained by alkaline hydrolysis of non-terminal gem dihalides. There are the examples like ethylene dichloride, propylidene chloride, toluene. When reacts with alkali, there are the products acetaldehyde, acetone and benzaldehyde respectively. Since the aliphatic gem dihalides are themselves obtained from alkanes and alkalones by the reaction of PCl5, so it is not very important for the synthetic point of view, and it is useful for preparing benzaldehyde. Gem dihalides can be prepared by addition of 2 moles of hydrogen halides to alkynes. Dehydration of vicinal diols. The famous name reaction Pinacol rearrangement. When 2,3-dimethyl-butane 2,3-diol, it is called Pinacol, treated with sulfuric acid, it undergoes dehydration involving rearrangement of carbon skeleton to give 2,3,3-dimethyl-butane 2-on known as pinacolone. This type of reaction vicinal diols yielding aldehydes and ketones is called pinacolone rearrangement. You can see in the reaction that 2,3-dimethyl-butane 2,3-diol, or we can say pinacol, when reacts with acid, there is a formation of protonated water molecule at 1 carbon. So, there is a formation of carbocation. Then there is a shifting of one group, or we can say 1,2-methyl shift, and then there is a removal of proton to give the pinacolone, which is 3,3-dimethyl-butane 2-on. Similarly, 1,1-diphenyl 2-methylpropane 1,2-diol on treatment with H2SO4 gives the product diphenylbutane 2-on. Here the protonated water molecule is formed at the carbon, which is more stable. We have already discussed about the reaction intermediates like carbocations, carbanions, free radicals, carbenes, nitrines in this lecture series, in which we have discussed the more the stability of carbocation or more the stability of intermediate, more will be the product form. Here at one carbon, carbon number 1, 2 groups are phenyl, on adjacent carbon there are 2 methyl group. So, protonated water molecule will form at that carbon which is more stable. Obviously, phenyl group attached to that carbon is more stable because of the delocalization of electron. Then there is a shifting of 1,2-methyl group and the removal of proton to give you diphenylbutane 2-on. The reaction starts with protonation of the 1-OH group, we have already stated. Isobutyraldehyde is prepared commercially from isobutene by the following sequence of the reaction that involves pinacol rearrangement. Isobutylene, you can see in the reaction when give you first of all isobutene glycol and then reacts with acid to give isobutyraldehyde. So, mechanism will be same. First of all, there is a formation of protonated water molecule at the carbon, first carbon, then there is a formation of carbocation which is more stabilized, obviously first carbon atom, then there is a migration of alkyl group and then removal of proton to give the isobutyraldehyde. Specific methods for aldehydes. Rosenmund reduction of acid chlorides. Aldehydes can be prepared in good yield by reduction of acid chlorides with hydrogen gas in boiling xylene in the presence of palladium catalyst supported on barium sulfate and partially deactivated by treatment with a small amount of sulfur or quinoline. The reaction is called, we have already told, Rosenmund reduction, and the deactivated catalyst is called Lindlar catalyst What is its importance? It does not permit further reduction of aldehydes to alcohols. So, we can see in the reactions acetyl chloride reduced to acetaldehyde, propionyl chloride reduced to propionaldehyde, benzoyl chloride to benzaldehyde, hex 4-ene 1 oil chloride to cis hex 4-ene 1L. Reduction of acid chlorides with lithium tri-tertiary butoxy aluminium hydride. Acid chloride with the lithium tertiary butoxyl aluminium hydride at 70 degrees Celsius in diglyme or in ether. So, aldehyde is formed in case of acid chloride, and when reduction of para-nitrobenzoyl chloride is formed, then there is a product of para-nitrobenzaldehyde. Stephan reduction of nitriles, addition of nitrile. What are nitrile groups? RCN group to a suspension of anhydrous tin chloride in diethyl ether saturated with hydrogen chloride. The resulting crystalline hexachlorostanate is collected and hydrolyzed by boiling water to yield the aldehyde. And these are the reaction. First of all, aluminium hexachlorostanate formed with the stannic chloride. Then there is a formation of aldehyde hydrolysis with boiling water. Benzonitrile will give you benzaldehyde, acetonitrile will give you acetaldehyde. Reduction of nitriles with diisobutyl aluminium hydride. You can see in the reaction that benzonitrile reduced to benzaldehyde, butane nitrile to butanol. Reduction of esters with diisobutyl aluminium hydride. Aldehydes can be reduced for esters of carboxylic acid with diisobutyl aluminium hydride. In the short form, it is called DIBALH, and reaction is carried out at -78 degrees Celsius in toluene solution. So, when we reduce methyl dodecanoate in DIBLH, it will give you dodecanol. Hydroformylation of alkenes, it is OXO process. Aldehydes can be prepared industrially by heating a mixture of alkene and synthesis gas, yani equimolecular mixture of carbon monoxide and hydrogen under pressure in presence of octacarbonyl dicobalt as a catalyst. So, propene when hydroformylate to give butanol and 2-methyl propanol. The reaction involves the addition of hydrogen and formyl group CHO across the carbon-carbon double bond. That is why it is called hydroformylation of alkenes. Another specific method which is usually for ketones are reaction of nitriles with Grignard reagent. We know what are Grignard reagent, RMGX. R is alkyl group. Ketones can be prepared in good yield by the reaction of nitriles. The catemine salt formed as addition product which is hydrolyzed with dilute mineral to yield the ketone. Here ethane nitrile when reacts with ethyl magnesium bromide, the addition product is formed which is hydrolyzed to give butane 2-oned. Another reaction, benzone nitrile will give first addition product and then hydrolyzed to acetophenone. Reaction of acid chlorides with lithium dialkyl cuprate and dialkyl cadmium. Ketones can be obtained by reaction of acid chloride with lithium dialkyl cuprate. It is called Oilman reagent, and you can see in the reaction that cyclohexane carbonyl chloride will give you cyclohexyl methyl ketone, and benzoyl chloride will give you acetophenone. Reaction of carboxylic acid with alkyl lithium. Lithium salt of carboxylic acid on reaction with alkyl lithium or phenyl lithium yields ketones. For example, you can see in the reaction, first of all there is a metallation reaction, then hydrolysis will give you the ketone from carboxylic acid. Friedel-Crafts, very famous reaction acylation of benzene. Aromatic ketones can be prepared by reaction of benzene with acid chloride in presence of anhydrous aluminum chloride as a catalyst. For example, you can see that benzene will give you acetophenone, or with acetyl chloride or with benzoyl chloride will give you benzophenone. And about the mechanism, first of all, there is a formation of electrophile which is COCH3, which is attached to benzene ring, and then product will be the acetophenone. And in case of benzoyl group, the product is benzophenone. Now, the next point of this lecture, physical properties of aldehyde and ketone. First of all, physical state. Formaldehyde, when we are talking about it, it is a colorless gas at room temperature. Acetaldehyde is a liquid, low boiling, colorless, which has boiling point 21 degrees Celsius. Other aldehyde containing up to 12 carbon atoms are colorless liquid. Ketones 3 to 11 carbon atoms are colorless liquid. About other aldehydes of low molecular mass possesses unpleasant smell, but ketones of low molecular mass have pleasant smell. Boiling points, aldehyde and ketones have higher boiling points than alkanes of comparable molecular mass. This is due to the polar character of the carbonyl group, which increases the intermolecular attraction in the aldehyde and ketone. The boiling point of aldehydes and ketones are lesser than the carboxylic acid and alcohols. Why? Because of intermolecular hydrogen bond in alcohols and carboxylic acid. Means when there is a possibility of formation of hydrogen bond, the boiling point will be higher, and in case of the compounds, when there is a possibility of formation of hydrogen bonding lesser, the boiling point will be also the lesser. You can see in the compounds and the respective boiling points with according to their molecular mass. So, greater will be the molecular mass, greater will be the boiling point. And hydrogen, you can see the hydrogen bond between carbonyl compound and the water molecule. Solubility, formaldehyde, acetaldehyde, acetone are miscible with water in all proportions because they form hydrogen bond with water, and the solubility decreases with increase in the number of carbon atoms. The carbonyl compounds containing more than 5 carbon atoms are practically insoluble in water. So, aldehydes and ketones are soluble in organic solvents like benzene, hexene, chloroform, carbon tetrachloride. The next important part of the aldehydes and ketones is reactions of aldehydes and ketone. The chemical reactivities of aldehydes and ketones is mainly due to the carbonyl group. The difference in electronegativity of carbonyl group is mainly responsible for the reactivity of these groups. The carbonyl group is highly reactive because of the polarized pi bond between carbon and oxygen. And following types reaction aldehydes and ketones will give nucleophilic addition reaction, nucleophilic addition elimination reaction, oxidation reduction reaction, and reaction involving alpha hydrogen of the carbonyl group. In the next lecture series, we will discuss about details the reactivity of aldehyde and ketones. The reactivity of aldehyde and ketones mainly due to the carbonyl group because of the electronegativity difference in carbon and oxygen and the pi bond between these two atoms. These are the responsible factor of the reactivity of carbonyl group. So, in this lecture we have discussed about the complete, I have tried to explain all the preparations of aldehyde and ketones, and in the next part of this particular lecture, aldehyde and ketone, we will discuss about the reactivity. Reactions of aldehyde and ketone. Thank you so much.
Thank you, ma'am. Thank you so very much for giving deep insight into this topic. As Dr. Vandana herself said that we would be continuing this lecture further in our next session, in our next lecture, and we would be discussing more. Thank you, ma'am. Thank you so very much. And I would like to tell you all that if you have any queries, you can mail us at info.cec@nic.in, so that the next time when Dr. Vandana comes, we would solve your queries in lecture itself. Thank you, ma'am. Thank you so very much.